Okay. I'll give you simple function RP. Two cosine Ti minus three sine Tj. Okay. What I want you to find is talk about finding velocity and the acceleration. And if you go ahead knowing what the tangent vector is, and if you haven't, that's okay. And that thing is a distorted A. Let me see if I can get a better thing. Okay, you might not know what this is, you might not know what this is, but we're gonna do it with a reason. Okay, I think we get these pretty instantaneously. So B is just a derivative. And that's gonna be written a little small, but negative two sine Ti minus three cosine Tj. Did I got it right? Okay, and then A is second derivative of R, even though it's gonna write the V, which is negative two cosine Ti plus three sine T. Okay. Okay, so let's, before we go on, what's the angle? I'll compute these kind of quickly for you, but just go ahead and give you a minute or two. Figure out at least one of the. Okay, let me just, if you did this at home, you got it right. Okay, angle between two vectors. Right. But when you do it, make sure you do it in a way that you're going to retain it and be able to use it. Okay, nobody. I saw it. Started with the right thing. Now, as soon as I said, well, use the definition of the dot product, oh, yeah, okay. And everybody wrote down the angle here. Do it, but I shouldn't have it blank. But that'll be a test coming up. Probably late next week. Okay. So you're gonna want to have this stuff at your fingertips. You don't want to get hung up in the middle of the test, having to think, how do I find the angle between two vectors? Okay, so you want to review, and I'd start reviewing now. Just go back and look at things. Oh yeah, I forgot that. Okay, yeah, this is important. Maybe I'm gonna make a note of it. Yes, spend a half hour doing that a couple of times a week. It pays for the benefits. Of course, before the test, you probably spend more than that much. Okay, so you got this, well, okay. Well, the dot product is -4 cosine t sine t plus 9 cosine t sine t over the product of the magnitude. Square root of now I have to bunch that up, and you just look at the thing and write these things down, okay? You know, magnitude is the square root of the dot product of the thing with itself, right? Or you can just think Pythagorean theorem, square this, add them up, take the square root, okay? So by the Pythagorean theorem, or by dot product, square root of the dot product of itself, you get this. That equals I cosine t sine t divided by the square root of, we can do the product of these two. Okay, you're gonna get square root of cosine squared t, and then you're gonna have 16 cosine squared sine squared 81 cosine squared sine squared 97 sine squared t cosine squared t. And then it's gonna be plus 36 sine squared t. And I should remember who that off. Not write down anything good. Okay. And then 36 cosine squared 36 sine squared t is 36. Okay. That's just the angle between B and T, or B and R. Now, if this thing is a circle, then these numbers smooth out. And you get a much simpler expression. Okay, because your coefficients here are both going to be the same. It's going to follow that B is always perpendicular to R, and that the acceleration is always parallel to B, but in the opposite direction. In other words, if it's a 2 and 2, then you'd have a -2 here and a +2 here. So we do the dot product of B and R. You get 0. You get a negative, you get a 4 cosine sine and a -4 cosine sine here, and a 4 cosine sine here, so that these numbers would equalize, and you get 0. Okay. So you want to look at these expressions and think about what it means geometrically. And think about what it means in the special case, and the one special case of an ellipse is where it's a circle. You have a lot of insight. Now, so there's your angle. If you sketch this ellipse, major axis will be 2, and your minor axis will be 3. So that we sketch the ellipse. 4 by 6 rectangle. If you sketch it as I advise you to do it, because it's really pretty easy to sketch at least in that if you do a square of a rectangle. Okay. Now, where do we start? The t equals 0. Well, we're at two I and zero J, right? So R of zero. Here. Okay. Well, about pi over two, since it's cosine of t and sine t. Pretty easy to just look at t equals 0, pi over 2, pi, 3 pi over 2, 2 pi, right? So at pi over 2, cosine is 0 and the sine is 1, that's going to be negative 3. So it's an I minus 3j. 0i and negative 3j. So we go around the ellipse now, we see that we're moving in this direction. If we think of this as motion in time. And then we have our pi here. And r of 3 pi over 2 here. So we're at this point at t equals 0, 2 pi, 4 pi, etc. Here we're at 0, here we're at t equals pi over 2. Multiply pi over 2 plus 2 pi, that's 5 pi over 2. So forth. We're here at t equals pi, 3 pi, etc. We're up here at, you can write it out, 3 pi over 2. And if you add 2 pi and 4 pi over 2, so it's 3 pi over 2, so 11 pi over 2 and all that. And that needs to be something you just know. Okay. So work it out, make sure you understand how to get times. And you see then that this thing is cyclically moving around this thing every 2 pi units of t. Okay. Okay. Well then, we can see, just say that at your 45 degree angle. Okay. So this would be a t equals pi over 4, you'd be here and so forth. Where are you moving faster? Where are you moving fastest? From here, here, and here. First point, second point, or third point? First point? Okay. What's your V function tell you? T equals 0, this is 0. And this is, cosine is going to be 1, right? So velocity is going to be like 3j. Okay. When you're down here, t equals pi over 2, so the sine is 1, and the cosine is 0, so it's going to be a negative 2i, right? Makes sense? Just plug the numbers, plug the quantities in. So our velocities are t equals negative 3j here. Equals negative 2i here, and so forth. Now, how would you prove that this is your maximum velocity and this is your minimum maximum? If that is the case, it is in fact true, there are ways you can see that. You would have to maximize the velocity function. take the derivative of this and set it equal to zero, find your critical points. Okay. So. Is unchanged. Well, you know, if you look at that, that doesn't occur. Equals zero. It occurs somewhere in between. It occurs when the cosine is 3/2 the sine. Because your velocity in this direction isn't changing a whole lot while this thing is nearly vertical. And you're picking up a y velocity as you go. So the hypotenuse of the triangle you get, if you want to get your velocity vector, builds faster due to the increase in the horizontal component than it decreases due to the small decrease in your vertical. Okay. So we can prove that what seems intuitive isn't if you look a little bit. Again, if you just look at the fact that this doesn't change much, but this starts changing. Okay. And you gotta look at which one has more effect really. Okay. And it turned out cosine of t was 3/2 sine, which of course is when the tangent is 2/3. Okay. Now the tangent is 1 at the 45 degrees, so it's going to occur, 2/3 of that angle, sort of in this direction. It's going to occur about that. Then this component starts decreasing, and from that one increases and gives zero velocity. Okay. So that's just an illustration of what you can think about if you actually think about these things instead of just answering questions. Okay. And if you think about it, then you can answer a wider range of questions and you understand it more deeply. All right, well, so superficial question is, given R, how do you find B in it? You just take the derivative, everybody did that on this instance. Okay. Find the angle between two of these vectors. Angle prompt. But as soon as I prompted you, told them to do, although you didn't want to write out the expressions. Okay. But that's part of it, right? So, just work on your reflexes a little bit. You'll be fine. Nothing you can't do easily, but you have to think of doing it. Okay. So you want to think of everything you could and then pick out what you need from what you could do and do what you need to do. If that makes any sense, I'm not sure. Okay. Now, an important angle is between B and R, and we'll draw a bigger picture and see. Okay. There'll be an angle that B and R. I mean, this angle is important. But it's a right angle here, it's a right angle here, and it's not a right angle any place else. Like here, 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 and here. And those are the only places where this dot product is zero, because the only way the dot product is zero is for the cosine or the sine to be zero. or both, if they come close, can be seen. Okay. Not only versus this. Should be pretty clear, isn't it? Not, I order, I can review a little bit. All right. Okay, now, your unit tangent vector. Well, I really do have a new picture. I'm working on doing, so. Okay. All right. Okay, so let's just draw bigger pictures. And make myself a little bit. Orange, something you can have. Um. So at a given point. You have the R. V vector is tangent to the curve, which is clearly at this point. Not in that correct. Okay, here's your V. Okay. So the V's on a different scale than R. Here's V. And you also have an acceleration vector. What's the direction of their acceleration vector? Well, is your velocity vector getting bigger here or smaller? I'm thinking it's getting a little bigger because of that angle where the cosine of t is 3/2 sine t down here. You have the same angle up here, be about here. So B is still increasing here because it's smaller here than it is here. Okay. So B is increasing, the magnitude of B, the length of the B vector is increasing here to here. Then it decreases a little bit from here to here and so forth. Check it out, make sure that's really so. So if we have an R of t plus delta t, then we would have a V of t plus delta t. Well, sign against it, like go against it. Okay, V is increasing so that your acceleration vector is going to have a component in this direction. The rate of change of V is positive. Okay. It's also turning toward the center, so there's a centripetal component to it. But it's not toward the center. The acceleration here is not toward the center. The acceleration looks something like this. Because it's speeding up. The only thing it was doing was turning toward the center, then the vector would be toward the center. Okay. Actually, that's a little bit of an overstatement. Something like that. Don't want to go into speak more of it. Acceleration is not parallel to your V vector. Unless these two vectors have not part of Z. Acceleration is not perpendicular to V vector unless it's not product of zero minus. I don't remember what I said. But when does that occur? Well, that occurs Yeah. With velocity. Okay. Okay, that's just a calculation. Well. What we want to look at is first the unit tangent. Okay, unit tangent vector is just a unit vector in the direction of V. Can you write down the unit vector in the direction of your velocity vector? Yeah. Figure two of these, square root of v dot root. And you also get by whatever you tell. So. That looks like this. Here. One of these is magnitude of v, the other is magnitude of. One of these is magnitude of r, one of them is magnitude of v, which is which. Okay, so I'm not sure what I've said, what I haven't said. But for to find a unit tangent vector, that's a unit vector in the direction of v. And unit vector in the direction of a given vector is divide that vector by its magnitude, right? So we find out that t equal, well, I'll write it out, and v equals -2 sine t pi minus 3 cosine t okay, divided by the square root of 4 sine squared t plus 9 cosine squared. And you get that magnitude either by the Pythagorean theorem, sum of the squares of your square root of the sum of the squares of your components, or by the definition v dot v, square root of v dot v. And v dot v is the sum of the squares of the components. Okay. Now, I'm going to tell you something, and it's good for your soul to work out this derivative. Because these are the nastiest derivatives anybody in their right mind wants to compute. Okay. M is called your inward normal. And it's the rate at which your unit tangent vector is changing. Okay. Now, you want to calculate that derivative? You should. My fill page. But it makes it better taking derivatives. And I wouldn't put it past me to put it on the test. Okay. Or something equally nasty. And that's a simple one. Okay. Fortunately, there's a shorter way to get the unit normal, but think about what it means. Unit tangent vector is in this direction, and then it's in this direction, right? So let's just do a unit tangent vector, a couple of unit tangent vectors up here. But the curve is kind of smooth. Well, it's not really all that smooth. But let's say this is t And of course, there's the R of T. And let's say that this is T of T plus delta. So here's R T. Here's R T plus delta T. And if you want to go to the bar, you can get different square for each of these things like we did last time. And you want to get used to that because we're going to do partial derivatives. It's much more complicated. It's not bad once you see what's there and learn to sort out all the notation. I think that's coming up. That's coming up. Okay. So you have these two tangent vectors. Well, I can move these two tangent vectors over here. I can see how much they change. So here is a picture of T, not on the lips, but it's still this vector, and this vector is for T of T plus delta T. Well, big T is a change in your unit tangent vector, which is this. Okay. And I claim that in the limit as little delta T approaches zero, as these things get closer and closer together, that your change in T is going to be perpendicular T. Okay. Now, why do I say that? These are both unit vectors. Here they are again. Then they form a triangle with the delta T vector. Okay, I'll even make that again. First place, it's obvious that that delta T vector is a chord of the circle, right? So it goes from a point on the circle to a point on the circle because these two vectors end on the circle. Okay. And a small chord on a circle is very nearly tangent to the circle. And tangent to the circle is perpendicular to the radial vector. So if I did a radial vector here, this would be very nearly tangent to the circle at this point, okay? But not quite because it's kind of cutting the circle a little bit. But as these things get closer and closer together, this thing becomes closer and closer to tangent, and the limit as delta T approaches little t, delta little t approaches zero. This becomes tangent to the circle. Now, one elegant way of doing that is to say that, okay, let's see, here we got the two there. And I'm sure that I'm often it's great when okay. Two vectors, both at length one. What kind of triangle is this? There's a name for it. In some places, they call it Billy Bob. Okay, so this is my isosceles triangle. There are two equal angles. They're not all equal, obviously. I mean, they could be. An equilateral triangles, that's awesome. But this is an equilateral triangle, the angle here that's gonna approach zero is delta two approaches zero, right? Now, as this angle approaches zero, what is the sum of these two angles approach? Not approaching 180 degrees, doesn't it? Because the sum of all three is 180 degrees, and if one of them is gonna approach zero, the other two gotta approach a sum of 180 degrees. These two angles are equal because of the symmetry and other arguments of this figure. If you flip the figure over this way, it's going to look the same. So the angles are the same. Right? Yeah, but this side of length one goes here, and this side of length one goes here. You still have a side of length one and a side of length one. Okay. But whatever angle is here is now here. Whatever angle here was here is now here. Since the triangle is identical, the angles have to be the same. It's a symmetry argument. Right, symmetry arguments you have to do here. Hold on to my jaw. I've got a very piece here. Now, that means that both of these angles approach 90 degrees. And in particular, that this angle approaches 90 degrees. That's an important argument. Important in physics. What's centrifugal acceleration? Is centrifugal. Okay. The acceleration is toward the center. Okay, well, the acceleration is perpendicular to this vector. But it's not centrifugal. For a circle, it would be centrifugal. In the ellipse, acceleration vector acceleration vector it's not acceleration. It's derivative of your unit tangent. Okay. This derivative of unit tangent vector is the limiting value of this difference divided by the time limit. Since this difference becomes perpendicular to this vector, the derivative of any unit vector, it remains a unit vector, it has to be perpendicular to that vector. So it's a derivative perpendicular to the vector. So by this argument, which you ought to review and bring it up to, okay? This is why the unit tangent vector, the derivative of the unit tangent vector is perpendicular. Wait a minute. I left off something important. I just right there was things that didn't seem to fix it. Okay, well, M is your unit normal. Okay, the derivative of the unit tangent vector is not necessarily a unit vector. It generally is not a unit vector. Okay, make it a unit vector. I scared you not by saying you got to do this derivative. Then you got to divide that derivative by the magnitude. So that's where you end up filling a page. Okay. It gets really, which seemed to me at the time really long. That's exactly, I've seen a lot of things that are even longer, much longer, but that was an interesting chunk. I thought it was really neat. Okay. Be able to take that and write out that expression at the time. That was reasonably challenging thing to do, pretty tedious. You had to do it right. Good for your soul to work out, at least for a simple function like this. All right. Now, if you're in three dimensions, you got a helix that's accelerating upwards. An elliptical helix that's accelerating. And along the ellipse. Okay. So maybe you have a t squared there, cosine of t squared, and sine of t squared instead. Derivatives get more complicated, the motion gets longer. Okay, well, what we really want to look at then, first of all, let me just show you the easy way to get the unit Norman. You're going to be surprised if there's a projection involved. Never be surprised if there's a projection involved. Okay, remember what I told you. It's one of those foundational features, one of those foundational things that occurs again and again and gives you a lot more insight. You can really understand the whole projection. Okay, so. Okay. There's a hard way to find the unit moment. The easy way to find the unit moment. Take your velocity factor. And your acceleration. Find the vector projection of the acceleration vector on the velocity vector. It's a projection on A of B. Now, think about it for a minute. How are you going to get a normal vector, a vector perpendicular to your velocity vector? Okay, first place, you'll have to digest what I told you last time. Okay, and you don't necessarily have time between Tuesday and Thursday to digest anything. You're just trying to keep your head above water. So no worry there, but I'm trying to make the point that you really have to understand projection. This is the third time we've used it. First time we learned it, and we used it, and we used it, and we used it again. Okay, so very, very important. And it needs to be understood as something more than just a formula. It's a picture. The picture tells you what the formula is, and the formula tells you what the picture is. I think it's easier to see the picture and use that to get the formula than it is to get the formula and figure out what the picture ought to be. Okay, but that depends. Yeah, some people see it one way, some people see it easily the other. Figure out which way is easier for you. Make it easier yourself. Okay, but relate the two. Okay, to the extent that it's possible. Now, the one suggestion somebody had was, well, just switch the X and Y coordinates of the I and J components, okay? And a negative percent, which means they have to do a negative number, okay? So, you know, if the velocity vector is this one that you thought is a negative 2 sine ti minus 3 cosine tj, perpendicular would be 3 cosine ti minus, or plus, yeah, minus 2 sine tj, or negative 3 cosine ti plus 2 sine tj. Okay, the dot product will be 0. And you want to check that out, see that the negative thing works. But that's in 2 dimensions. What are you going to do in 3 dimensions? What are you going to do if you go beyond 3 dimensions? Okay, dot product is defining any number of dimensions as you learn in linear algebra. Okay, and you use it in linear algebra. And then in deep data analysis, you deal with spaces that have millions, even hundreds of millions of components. You can still do it. Okay, and you have a topology, you have shapes that occur within your data, and I'm no expert in that. I haven't had my hands on it. Good for the data. Lucky for the data, but you know, nobody needs more to look at it. I don't know enough topology. Okay. I know some topology, but I don't know it at that level. Okay, a few people do, even mathematicians. Okay. So my point is, doing a negative reciprocal only works in two dimensions. You want to scale any number of dimensions as you do in the real life. And as we can do with multivariable calculus, it gets kind of complicated when you go to dimensions. Complicated enough in three dimensions. That's all we're going to do. Okay, so what you do is, I just subtracted the projection from the acceleration vector, like we did last time. Because right here, this is perpendicular to this. So if you did this and add this, you're going to get this. So if you do this and subtract this, you're going to get this vector. It's going to look like it's over here, but it's working from edge to tail. So you get your acceleration vector. This is a right angle. You have the negative projection vector. I'm not going to write out the age that we have here. And this is parallel to this because that same vector would work in this triangle. So that this is perpendicular, so that your normal vector, a normal vector, really kind of small, but a unit normal could be any normal vector divided by its magnitude. And this is the vector we use because it's called the inward normal. Okay. And that relates to concavity and stuff like that. When it's concave this way, so the inward concavity would be here. Okay. Make sense? Okay, well, now that we have that, we can calculate the components of A, tangent and normal. Go back to the original questions. Okay, your tangent vector is just okay. And I don't have room to write it, but I will here. You want to see it again? Well, together. Okay. Your component of acceleration in the direction of your unit tangent vector. Well, go back here. Here's your acceleration. Here's your unit tangent vector, right? How do you get the component of the acceleration direction of the unit tangent vector? You project it. And you get a component that I'll draw here. They didn't remember very well, but that's A sub T. And then you have a vector here. It's A sub M. Actually, I don't need to put that arrow over the subscript. Okay. And what's A sub T? It equals. Just A dot T. Just when you project on a unit vector, you don't have to divide by the magnitude. The magnitude of the unit vector is one. Okay? And you really want to kind of focus on that. It's another idea that saves you a lot of thinking and a lot of trouble when you forget it. Okay? Sometimes you just that needs to be second nature. Make sure you work it out. You don't have to remind yourself. And unless you're a lot smarter than I am, so you probably are. You have to think through these things repeatedly before they become second nature. Like the thing about the projection, okay? Got to keep reminding yourself. When you do a derivative, you got to keep reminding yourself it's a limit of something at t. Difference between the value of something at t and a t plus delta t divided by the delta t. Okay. Anyhow. Normal component can be calculated just by A dot M if you calculated the unit normal, which you normally want to do. Or just using the same picture we've used 3 times now with projection, acceleration vector minus its projection on the tangent vector. Okay. And it's all right here in the picture. Try to see everything there is to see. Now, everything that we've done here works just as well if you have a vector with 3 components. Matter of fact, it works just as well if you have a vector with 30 components or 3 million components. Okay, you got 3 million components. You probably don't want to do it by hand. It's even worse than this. Yeah, that's where you program use a program that deals with. That's pretty much it. Again, I normally looked at this earlier. Let me just take a quick look if this thing's still. Active, and I don't know what it. There gotta be a way to go home. Home. Classes, assignments, questions, grades. Oh, here we go. Just back to Math 265. It's like it did something. Okay, looking. If I wanted to find the arc length between, let's say, this point and this, where I know what t is here and what t is here. Okay. What would I do? So in general, about a curve that looks like this doesn't have to be or like this. Okay, about R of A, R of B, here's the R. In order to determine the arc length, you have to do an integral. You know that from the first semester, first year of calculus. You know, integrate the square root of 1 plus a prime squared. Okay. You do something analogous here. First of all, you just take, let's say this is R of T. R of T, this is you have R of T I here. R of T I plus one here. Trying to find this distance. Do you should take R evaluated at Ti star. The Ti star is between Ti minus one and Ti, and this I should be using Ti minus one, Ti minus one. Now, is that halfway familiar to, I mean, partition and interval? Right, the partition and interval. Okay, and Ti minus one is less than Ti at some point, you know, maybe that's in here somewhere. Maybe this is 100 miles long, there's a Ti minus one and Ti for any I you want to choose, right? So there's your basic Ti minus one to Ti interval. And you choose a sample point within that interval. Okay. Here's the interval. Typical interval. The I interval with the I sample point. At this sample point, you calculate the RDT. Okay. Then the approximate length of this interval here we'll let a script L stand for arc length. It's approximately equal to magnitude of your velocity vector times your delta T sub I, delta T sub I being T minus Ti minus Ti minus one. Okay, and of course that equals okay. That makes sense. Because multiply your velocity vector by your time interval. Multiply velocity by the time, you're going to get the distance. Okay. Then total arc length A to B is approximately equal to the sum of the distances you move in an individual interval. Now the key is to understand what happens in a typical interval. First, you partition the interval from A to B, where A is your parameter, A's value of T, B is the value of T. You partition it, then you just ask yourself what happens in a typical small interval, and then what happens when all your intervals shrink to zero. So the total arc length is the sum of all your arc lengths. That would be like life is going to end. That's a sum of I equals 1 to n of And when I said DRDT, it was LDT9, your DRDT is evaluated at your sample. With the sample point in there, I did put it in there. In any case, this approaches the interval from A to B from the magnitude of DR. DT. Now, this whole idea of partition your interval, or partition your area, or partition your volume. Something should be familiar to you from college. You might want to go back and review how very much some were set up and so forth. Just make sure you provide yourself with notation. But this is how we build intervals. Okay. And consider locally what happens. Put a small interval above parameter. Okay. Or parameters if we have more than that. But this could be anything. We write that down and then we sum it up and that approaches. And we don't get as rigorous about that as we used to, but we at least understand that the interval was developed by what happens over time. Okay. And typically, and there's a formula for argument. Yeah. Okay.